with the term of knowledge graph, but I suspect you have benefited from one, maybe even today. Take your favorite virtual assistant. Did you know that when you ask a question like, what is the capital of Canada? The assistant is pulling the response, Ottawa in this case, from information in a knowledge graph. Knowledge graphs can be seen as a way of representing semantic information between two entities. And what's really cool about them is that modern applications allow almost any entity you could imagine to be described within one. For example, we could have a knowledge graph of movies and actors, or we can describe ingredients for recipes as well as the steps required to cook them. And this means machines are able to understand how these entities relate to each other along with their shared attributes. And this allows us to draw connections between different things in the world around us. Now, a knowledge graph is made up of nodes and connected by edges. Nodes describe any object or person or place, and an edge defines the relationship between the nodes. So, for example, a node of Ottawa and a node of Canada might be connected by the edge of capital. And the thing here is that the pair of nodes, they can be connected by more than one relation if the two are related in multiple ways. So for example, let's take another city. Let's take Paris. Now, Paris is the capital of France, but it is also part of the Roman Empire, or it did used to be. So in this case, the edges are Paris to France is capital, and then Paris to Roman Empire is city of. And we can see then how that these nodes can be connected with multiple edges as we expand this. And knowledge graphs can sort of build different data sources and bind them together to infer missing facts. So let's say you're trying to predict the number of Chinese restaurants in New York City. You could use one data source, let's say census data, but that might not tell you the whole story. It might be out of date, it might not classify everything correctly, and so forth. So if we add a second data source, like say online reviews about all the different restaurants and put them all in a knowledge graph, then we can use statistical methods to infer that actually there are 2,900 restaurants serving Chinese food in New York City, which may be a lot different than what was reported in the census data alone. Now, knowledge graphs utilize something called natural language processing, or abbreviated to NLP, to construct a view of nodes and edges through a process called semantic enrichment. I can take some unstructured text, say a white paper, and classify that text using natural language processing to really sort of create data sets which are correlated and related to that information. And what that builds for me is a knowledge graph. And beyond sort of helping with question and answer queries, there are a lot of other commercial applications for knowledge graphs. So for example, the recommended videos that are probably appearing alongside this one in YouTube right now, well, they leverage a knowledge graph based on queries people are searching for and other videos that they might enjoy. In insurance, you can use knowledge graphs to sort of make sure that a given claim for damage is actually a true claim, or whether it's been one that's reported by a policyholder for fraud. And in retail, knowledge graphs can assist understanding the relationship between products so that companies can recommend different pairings that might be of interest to customers. And I'll leave you here with some wisdom that I was acutely aware of last night, and I'll share it in knowledge graph form. It consists of 3 nodes. There's human, then there is coffee, and then there is sleep. And these nodes are connected, of course, by edges. The edge between human and coffee is consume. The edge between human and sleep is needs. And what I learned last night, the edge between coffee and sleep is prevents. Avoid caffeine after 5 p.m, folks. If you have any questions, please drop us a line below. And if you want to see more videos like this in the future, please like and subscribe. Thanks for watching.
Today, I'm going to show you how to populate a knowledge graph and query it using an LLM. Graph Retrieval Augmented Generation, or GraphRag, is emerging as a powerful alternative to vector search methods. Instead of using a vector database, GraphRag systems store data in the format of a knowledge graph, using a graph database. In a knowledge graph, the relationships between data points, called edges, are as meaningful as the connections between data points, called vertices, or sometimes nodes. A GraphRag approach leverages the structured nature of graph databases to give greater depth and context of retrieved information about networks or complex relationships. The first step in setting up our system is creating and populating the knowledge graph. We'll be using an LLM to assist in creating the knowledge graph. Given unstructured text data, the LLM will extract entities and relationships from the data, transforming the data into structured data, which can then be inserted into the knowledge graph. After the knowledge graph is created, we'll be using the LLM to query data from the knowledge graph and return the response in natural language. Cipher is the query language for a graph database. When a user asks a question in natural language, the LLM will generate the Cipher query to extract that information from the knowledge graph. The Cipher query then gets executed on the database, and the results are returned to the LLM. The last step is for the LLM to interpret the results of the Cipher query in the context of the natural language question and return a natural language response. For this example, we'll need an API key and project ID. The link to this notebook is in the description below. In the notebook, you'll find instructions for retrieving these credentials. We'll be using Neo4j, an open source graph database, but any graph database can be used to create the knowledge graph. We'll create a local instance of the database using a containerization tool. I'll be using Podman, but you can use any containerization tool, for example Docker, as long as it allows you to create a Neo4j instance. If you don't have a containerization tool already, take a moment to install one. After installing, initialize and start a machine. My machine's already initialized, so I'm just starting it here. Once you have this running, you can start a database instance with this configuration. We need credentials to access the database, so I'm setting a name and password here. We also need to include the APOC library as a plugin in order to enable additional functionality for working with data and graphs. It looks like our graph database is up and running now. It's a good practice to create a fresh virtual environment for this project. I'm using Python 3.11.3 here. In the Python environment for your notebook, install the following Python libraries. We'll be using the OS and GetPass modules to set up credentials. We'll use LangChain's document class to store the text for input into our graph database, and the LLM graph transformer to create a graph from our text input. To interact with and query the graph database, we'll use the LangChain Neo4j module and its accompanying Graph Cipher QA chain class. To craft our prompts for the LLM, we'll use LangChain's prompt template and few-shot prompt template. We'll use the LangChain IBM and IBM WatsonX.ai modules to interact with the LLM and to set the parameters for our models. We'll need to set up our credentials using the API key and project ID that we retrieved earlier. We'll also need to set the URL from which we'll access these services. Now that our environment's set up, we can create the knowledge graph. First, we need to create a connection to the local database instance that we started earlier. Next, we define our data for input into the knowledge graph. In this case, the text describes employees at a company, groups they work in, and their job titles. We'll use this set of relationships to test the graph generating capabilities of the LLM. But you don't have to limit your data to straightforward examples of relationship data. GraphRag systems have been shown to be successful in retrieval and summarization tasks for far more complex narrative and connected data. Now we'll configure our LLM, which will generate text describing the graph. The LLM temperature should be fairly low and the number of tokens high to encourage the model to generate as much detail as possible without hallucinating entities or relationships that aren't present. One of the most powerful LLM use cases is transforming unstructured text data into structured data. The LLM will transform our text input string into a structure of nodes and relationships that we can use to populate the knowledge graph. The LLM Graph Transformer allows you to set the kinds of nodes and relationships you'd like the LLM to generate. Restricting the LLM to just those entities makes it more likely that you'll get a good representation of the knowledge in a graph. Given our text input, we set the allowed nodes to person, title, and group. We also set the allowed relationships to title, collaborates, and group. We use the document class to prepare our text to be added to the graph documents. The call to convert to graph documents generates text in a format that represents the entities in the graph. We can inspect this graph documents object to see how the LLM generated nodes and relationships from the text, representing the relevant context and relevant entities. Now that we have the data in the correct format, we can insert these nodes and edges into the graph database using the Add Graph Documents method. Once the graph data is created, we can visualize it using our browser. In order to query our graph database, we'll use Cipher queries. Cipher is for a graph database what SQL is for a relational database. Instead of operating on tables, Cipher queries operate on the nodes, relationships, and paths in the graph database. To visualize the graph in the browser, I ran this query which shows us all the nodes and relationships in the graph. On a larger knowledge graph, this visualization might be too complex, but for our example, it works to verify the structure of the graph. It looks like the relationships in our input text have been correctly represented here in the knowledge graph. We can also examine the schema and data types in the database using the getSchema property of the graph. Without the LLM, creating the knowledge graph might be a manual process to diagram entities and relationships from unstructured text. Now that we have our knowledge graph, we can query it, taking advantage of the graph structure and graph database retrieval capabilities to derive valuable information over the data in a more holistic way than semantic search can perform on a vector database. Now we'll use natural language to query the knowledge graph. The natural language query will be passed to the LLM, which is going to translate the query into Cipher syntax. This Cipher query will be executed on the database, and the result will be returned to the LLM using natural language. Prompting the LLM correctly requires some prompt engineering. We'll think of the prompting step in two parts, so we'll need to set up two different prompts. The first prompt gives the LLM instructions for generating a correct Cipher query from the user's natural language query. LangChain provides a few-shot prompt template, that can be used to give examples to the LLM in the prompt, encouraging the LLM to write correct and succinct cipher syntax. This code block gives several examples of questions and corresponding cipher queries that the LLM should use as a guide. It also constrains the output of the model to only the query. An overly chatty LLM might add in extra information that would lead to invalid cipher queries. Using a prefix with a specified task and instructions also helps to constrain the model behavior and makes it more likely that the LLM will output correct cipher syntax. The second prompt provides the LLM instructions for translating the result of the cipher query into natural language, given the original natural language question from the user. We employ a few-shot prompting strategy here too, providing examples to the LLM for how to do this. We call this prompt the QA prompt. Essentially, it describes how the LLM should answer the question with the information returned from the graph database. Now we'll bundle together our cipher prompt, our QA prompt, our knowledge graph, and an LLM to create the question answering chain using the graph cipher QA chain class. We're implementing a simple retrieval procedure here, but there are ways to improve on this strategy by providing additional context to the LLM about groupings and summaries of like nodes within the knowledge graph. Using a temperature of 0 and a length penalty encourages the LLM to keep the cipher prompt short and straightforward. If you're wondering why we're configuring a different LLM here, it's because we're setting different parameters for retrieval of information from the graph than we used earlier for constructing the graph. Now we can query the data by invoking the chain with a natural language question. If you try this out, your responses may be slightly different than what we're seeing here because LLMs are not strictly deterministic. Here's our first question. What is John's title? We can see the cipher query generated by this LLM to retrieve the information, the result of the cipher query, and the natural language response from the LLM as director of the digital marketing group. Looks good. Let's try a slightly more complex question. Who does John collaborate with? Again, the LLM generates a cipher query to retrieve the correct information from the graph database and returns the correct response. John collaborates with Jane. This looks good. Let's ask the chain about a group relationship. What group is Jane in? Jane is in the executive group. Okay, let's try one more that requires the LLM to give us two outputs. Who does Jane collaborate with? Jane collaborates with Sharon and John. Even for this more difficult query, we can see the chain correctly identifies both of the collaborators. Beyond retrieving the simple titles and relationships from our input string in this example, GraphRag can summarize and retrieve contextual information over the whole structure of the knowledge graph. So how is this different from a vector RAG system? Firstly, instead of calculating embeddings and storing the resulting embedded information in a vector database, a GraphRag system transforms unstructured text data into structured data using an LLM, and a knowledge graph is populated with this data. The second difference is in the retrieval step. Instead of performing semantic search and returning results with semantic similarity, the LLM generates a cipher query in response to the user's natural language query, which gets executed on the graph database containing the knowledge graph. The GraphRag system avoids one of the limitations of vector RAG. If you think about the way vector RAG returns top semantic search results to a query, you can recognize that vector RAG can't provide the LLM with knowledge over the whole text corpus in response to one query. It's limited to the top semantic search results. GraphRag can leverage graph indexes, which store summaries about groupings of like nodes, to provide summarization over the whole corpus of text within one query result. In practice, you may want both the capabilities of retrieval from a semantic search on a vector database and a graph search over a knowledge graph. It's possible to build these sort of hybrid RAG systems using both vector databases and graph databases. Check out the GitHub link in the description below to try out GraphRag for yourself.
AI agents have different ways to remember stuff, and each serves a different purpose. So let's take a look at the 4 main types of AI agent memory, from some pretty foundational stuff to what I think are some quite interesting emerging areas. And I think it's really, first of all, worth considering how we do it. How does human memory actually work? Well, we can think of human memory as having, well, first of all, short-term memory. So that's the stuff that is active in the brain right now, like what I'm saying at this very moment. That's one type of memory. But there's also a type of memory called factual knowledge. So this is things like the company security policies that you remember, or it could be facts like Python is an interpreted language. Then there are learned skills, like, I don't know, writing backwards on a sheet of glass, for example, which I am totally doing here. There is absolutely no camera trickery involved. And then there is personal experience. Like the time I spent 3 hours debugging a Kubernetes cluster only to discover I was pointing at the wrong cluster the entire time. Seriously, that was 3 hours of my time. Anyway, it turns out that well-designed AI agents, they also need these 3 types of memory, or these 4 types of memory that I've got here. And there's actually a well-known framework for this, and it's from a Princeton research team, and they gave it the name of Koala. That's Cognitive Architectures for Language Agents, and Koala maps out 4 distinct types of memory that agents need. So let's walk through each one and see how they actually work in real agentic systems today. So type 1, that is working memory. This is the agent's context window. It's everything the agent can see right now. The current conversation, if there's any system instructions, they'll be in there. If there's any files or data that have been loaded into the prompt, that's where they'll be as well. So it's really kind of the scratch pad. And the analogy everybody uses for this is just like RAM, random access memory. It's fast and immediately accessible, but it's volatile. When the session ends, it's gone. And it's also limited in size. I mean, the biggest context windows available today are pretty big. I mean, it could be like 1 million tokens or even more than that, but that still has a ceiling. And try to stuff too much in there and performance is going to degrade as the model starts losing track of things that are kind of buried in the middle of the context window. So every agent has working memory, but then so does every chatbot. It's just the context window. So the question is, what else do agentic systems need? Well, let me add to that list, number 2, semantic memory. And this is the agent's knowledge base. So semantic memory stores facts and rules and conventions, documentation. And in the academic literature, this often gets described in terms of things like vector databases or as knowledge graphs. And yeah, those are real implementations, but in a lot of production agentic systems today, semantic memory is something much simpler than that. It's just simply markdown files, .md files. So take Claude Code as an example of this. So it has one of these markdown files. Its one is called claude.md, and that sits in the root of a project. And that file contains the project architecture, the coding conventions, the build commands, what frameworks to use, and also what not to do. And that file gets loaded into the context window at the start of every session. So semantic memory tells the agent what it needs to know in general. And without it, the agent is, well, it's kind of destined to make the same mistakes over and over again because it has no persistent knowledge to draw from. So working memory, semantic memory. What else is there? Well, number 3, that is procedural memory. Now, procedural memory is how the agent knows how to do things. And there's an open standard for this that's called Agent Skills. And it uses a file format called skill.md. Now, a skill is just a folder with a markdown file that describes the skill and what that skill does, and some step-by-step instructions for how to perform that skill. And it could be anything from creating a PowerPoint presentation to running a structured code review. Now, skills use something called progressive disclosure. So the agent doesn't load all of its skills into the context window, or I guess I should say into the working memory at once, because that could blow through the working memory budget if there are a lot of defined agent skills. So instead, the agent just sees a lightweight index, which is just the name and the description of each available skill. So maybe that's 100 tokens per skill. Then when a task comes in that matches one of these skill descriptions, the agent loads the full instructions. And if the skill references other stuff like other files or templates or scripts, well, those only get pulled in when the agent actually needs them during execution. So the agent advertises what skills it has, it loads the instructions in when they're needed, and then executes with the additional resources pulled in as they're needed as well. And all that is quite different from semantic memory, where the knowledge is always present in context. All right, number 4 is episodic memory. And episodic memory is the agent's record of what happened in past interactions and past decisions and what it learned from them. Now, a naive implementation of this is just to save every conversation transcript and then just search through them as you need to. And that technically counts as episodic memory, but often that's not very useful. So what production systems actually do is a bit more like distillation. So as the agent works across sessions, it kind of accumulates notes for itself, but it doesn't save everything. It decides what's worth remembering based on whether that information would actually be useful in a future conversation. So the result is distilled or compressed experience. So things like, last time we debugged the auth module, the issue was in the middleware layer. That's something that's a lot more useful to remember than just a full transcript of a 45-minute debugging session. And this is where memory starts to kind of genuinely look like learning, because the agent is going to get better over time. But episodic memory is also the hardest type of these to get right, because what do you delete? When does information become obsolete? If a user changes jobs, do you keep the old project memories around? Or should we forget them? Well, humans are actually pretty good at forgetting. I do it all the time. And as frustrating as that can be, it can be quite useful. But for agents, forgetting is an engineering problem. So 4 types of memory: working, semantic, procedural, episodic. But not every agent necessarily needs all 4. Let me give you an example. So let's say we're building a simple reflex agent. So that's something like a thermostat or just like a basic routing bot. Doesn't need all 4. It might only need access to working memory, the context window, and that's basically it. Now, if we take something a little bit more complicated, like a customer support agent, but one that's still fairly simple and narrow, like an agent that resets passwords, for example, well, that will still have access to the working memory, of course, but it probably also needs access to procedural memory as well, because it needs to recall the password reset skill, but that might be it. Whereas if we take a look at something like a coding agent, it probably needs access to all 4. So it certainly needs access to the working memory, the context window, but it also needs the product knowledge it would get from semantic, and then the skills system from procedural, and also the auto memory from episodic that learns across sessions. So memory is really what separates a chatbot from an agent, because a chatbot gives a response, but an agent can give a response shaped by persistent knowledge and accumulated experience. It remembers the project, it remembers preferences, and a good memory architecture also remembers the mistakes, so we're not destined to repeat them, which honestly would have been wonderful if an agent had told me about that Kubernetes cluster before hour 3. So 4 types of AI agent memory. Which of these are you using in your own agentic workflows?
Artificial intelligence is set to transform IT. Yesterday, I asked AI, how many AI agents are being created every day? The answer was 11,000 per day based on news releases and other public sources. At that pace, we'll have over 1 million new AI agents deployed this year. While there's no way to know exactly how many AI agents are being created each day, chances are that you will be asked to work on a project to develop AI agents or to begin working with an orchestration platform to work with orchestration of complex workflows in your environment using AI agents. There's some good news. Orchestration of workflows with agents are in many ways an extension of some of the established frameworks and tools that most developers have worked with before. Today, we'll take a look at how agent orchestration is fitting into the existing IT ecosystem. Okay, now the big new kid on the block are these GPT models that are allowing us to have these large language models. And what we're seeing with the LLM is that we're bringing in a strong language faculty that is allowing us to open up the kind of logic that we're dealing with when we're automating business tasks with technology, right? So we know that the LLMs are trained on massive text data sets. They understand human language. And so this is a really nice component to pull into our design framework when we're building software. So some of the really common software that we're dealing with is broadly assistants, okay, and agents. And the simple thing to remember about assistants and agents are that they're actually very similar, but assistants are going to really be driven in a prompt response framework, right? So, we ask a question, it's called a prompt, and then we get basically we get an answer, a response, okay? Now, with agents, agents don't really need to be prompted in this way. So with agents, what we're really doing is we're talking about defining goals, and then what we want out are outcomes, okay? And so again, assistants, we're sort of asking questions and looking for answers. Agents, we're defining goals and we're looking for outcomes. Now, the really big difference here is down to the definition of the word agency. And agency means that we are giving the software agency to actually take action at its discretion within the boundaries that we set. Whereas an assistant is just going to sit there until it's prompted, right? And then it's going to be at the ready to answer us when we prompt it, okay? So remember that when we're developing assistants and when we're developing agents, there's a lot of new buzzwords. There are sort of small language models, large language models, constrained language models. With agents, there are a whole bunch of different design decisions that we make. But at the end of the day, it's very important to remember that this is software, right? And so experienced software engineers should come into this space with some confidence that you can bring all of your best practices and past project experience, and all of those same things are going to serve you very well. So most of the developers that I interact with have mentioned that once they really jump in and get started, working with assistants and working in these agentic frameworks, that they're able to make progress quite quickly, and have a little bit of fun as well with these new technologies. So I was having a conversation recently, maybe a little bit of a debate, with a friend of mine, and we were talking about agents and orchestration layers. And my friend said, "Hey, what is different about an orchestration layer? Is it really just robotic process automation with LLMs added into it?" And I thought that was an interesting take. So interesting that I think when we're talking about people who are building things and talking about things, we often like an example. So let's imagine that we have a business process here with 3 steps, and obviously the 3 steps here are going to be supported by technology. And let's talk about what it would look like to bring an orchestration layer into this process. And so the first thing we want to remember when we're talking about orchestration, so we have a flow like this. And when we talk about orchestration and agents, we just said a moment ago that we're bringing LLMs into place. What I'm going to do is I'm going to create a little triangle agent here. This is an agent. And we said that, agents have LLM capabilities. And we stressed that we're talking about goals and outcomes. Okay? So let's take an example of a process where, the thing that we want out is a customer quote, so an actual quote that we can send to a customer. And the thing that we're putting in is a goal. Okay, and the goal is to create a quote. So we want to create a commercial quote that's good enough so that our sales team can send that quote out to a customer and not get us in trouble with all the finance people and the product people. So the way to think about orchestration versus robotic process automation. Okay. So, ultimately they're similar in that we want to understand our process. So in this case, it's kind of left to right. We want to understand our process and we want to boil this down into a really, really tight job story so that we understand if we want to create a quote, what has to happen so that we get a quote on the other side that's conforming to all of our desires. So in the old days, robotic process automation would typically have to interact with, let's say the first step here is maybe we have an application like a CRM. And this is where we kind of understand, where we are in step in a sales process. And this is where we know when it's time to create a quote. Okay. Now the API would probably have a difficult time discerning when it's time to make a quote, unless we had a really strong programmatic step built in here where we click, make a quote or something. It would have to be really obvious, okay? Because through the API, we're gonna be able to access very specific actions, almost like calling a software process. And we're gonna be able to access very, very specific structured data. So usually data tables, or keyword pairs or things that are very structured in the RPA framework, okay? So after we go in here, let's assume we can go in here and we can detect when we need to create a quote. And let's say that we can also retrieve valuable information like the customer name and the customer address and some of the other, particulars that we're gonna need along the way here to get over here where we wanna get to our quote. So then let's say the middle process is something like, product SKUs, and maybe product catalog. Okay, so here maybe we have a database of approved product SKUs, and that maybe we have a separate database that's kind of in this container that's going to give us detailed product catalog and more descriptions of those SKUs. And then lastly, over here, this might be some kind of sort of financial application or financial container that knows how to look at what we pull together and sort of, correctly put prices on things. And then maybe there's also sort of a legal container or legal information in this container where we kind of know our T's and C's that we want to attach based on the combination of SKUs that we put together. Okay, so this is kind of a very simple cartoon of a process where we're trying to, when we want to create a quote, we want to leverage, a CRM application, a data source that has product SKUs and product catalog, and then we want to get into some kind of financial application that can price SKUs and also apply legal T's and C's based on those SKUs. Okay, now in the RPA world, what we're going to need is we're going to need APIs and kind of really well-defined data tables into each of these resources. But we're probably going to run into some real problems when we try to do this use case, because we're going to really need to make sure that all of our applications are configured in ways that are very, very highly structured and that really provide us explicit triggers and explicit structure around this problem. So probably not impossible, but if any of you have tried to use RPA to do something like creating quotes for your sales team, drop it in the comments and tell us how it went. I'm sure there's some interesting challenges that you've run into. Now, when we go to the orchestration, we suddenly have agents, okay? And the beautiful thing about agents is that we can have many of them, okay, that are going to be working together. So with the agents, we're going to create, in reality, let me make sure I have my agent color still the same here. In reality, we're going to make, we're probably going to make an army of little agents, right? So agents, do really well when we keep them kind of narrowly defined and keep their job stories really, really tight. So because we're going to give these things agency, and that means we don't want them to get off the rails. We don't want to hand these things LLMs and give them a big scope and have these things doing a lot of things that are not useful. So we're probably going to have kind of a master agent for this process that the orchestration layer is going to leverage to then delegate parts of this overall process to this little army of agents we're going to end up with over here. So when we're orchestrating we want to create a quote. So now each of these resources, like our CRM, for example, our CRM is going to need to become an MCP host. And it's going to need to spawn an MCP service, very similar to down here. We're in kind of a client-server architecture, so not much is changing in terms of the overall framework. But now that we have this MPC service, we can kind of spawn our agents. This might be our master agent, and then our master agent, we're going to get a little fancy with the artwork here, sorry. And then our master agent, may spawn agents 1 and 2 that are really well trained on how to dive through this MCP service in this hosted area. And these two agents are really good at evaluating where we are. So this first agent might be able to evaluate, and identify, hey, we're in the right step of the process to create a quote. So this agent may say, yes, we need to create a quote for this specific opportunity. And then agent 2 might be a grabber agent. So when agent 1 says, yep, this is time to generate a quote, a message may be sent to agent 2, and agent 2 may go in and grab, customer name, customer number, customer address, and then may pull documents that have been attached into the CRM workflow to pull out, what products and services have been discussed with the customer, and what does it look like we need to pull together for a quote. That information then comes back and can be checkpointed in the orchestration layer, so that now these agents, agent 1 and 2, have now done their job and they're released and they go away. What we've done is we've cached some context data so that now we launch our sort of captain agent here. Now launches agents 3 and 4, and agents 3 and 4. Try to keep my colors the same here. This is now an MCP we're going to need all of these things to be MCP services, okay, so that our agents know how to talk to them. And so basically the agents 3 and 4 are going to dive through the MCP of ultimately a data source. So now instead of lots of tools, we're describing really specific data sources around product SKUs and product catalog. So agent 3 may be designed to go take a look at the data that we fetched, that agent 2 fetched, and then say, okay, I know how to take the data that agent 2 fetched, and I know how to go in here, and I know how to interpret the product SKUs so that now I can pull together a list of SKUs that I believe satisfies the requirements for this customer. And then those may be handed off to agent 4, and agent 4 may know how to come in here and navigate the product catalog. So agent 4 says, I've got to go into the product catalog, and I've got to check and make sure that the list of SKUs that agent 3 gave me all work together and that we can ship them together. So I might be checking compatibility. I might be checking, legal constraints or commercial terms. I may even be doing really higher level logic, like checking against whether or not these SKUs are aligned with the current product goals, sales goals, etc. So really, this can get quite complicated and can become much richer than what we used to think about, down here in robotic process automation. So now these agents 3 and 4 come back, and they add some more data into our story up here. So over here we got some like customer info and a list of what we thought needed to be in the quote. Over here we started adding useful stuff like we got SKUs that we think we need to go in the quote, and we did a lot of checks around whether or not these SKUs go together off the product catalog and against sales goals. And then we move forward and say, okay, now we're moving into this financial legal T's and C's area. So again, our little master agent knows where we're at. 3 and 4 are released. And now we need green again. And now we move into agents 5 and 6. So we call in our agent 5 and 6 team. And again, we dive into the MCP service, into our financial and legal terms and conditions catalog. Okay, now our legal department, has already set up this data source for us and has vetted it. And our financial teams have already vetted, our pricing, etc. Now, our first agent 5 may come in and knows to take our SKU list and come in here and agent 5 prices our SKU list. Okay, so agent 5 is pricing. And this probably involves, inferring or looking at sort of some notion of quantity. And then agent 6 may come in and understand how to interpret our legal catalog. And so when agent 6 comes in and interprets the legal catalog, we pull together, the terms and conditions and those sorts of things. So now agents 5 and 6 come back up here, and we've added some data. I guess I didn't write the word data, but this is all data up here. So we've added some pricing, and we've added some legal T's and C's. And now you can the story is kind of writing itself at this point, right? So now, what can we do over here? Well, we know the customer name, we know the customer address. We know, we probably know some of the details about what's been agreed between us and this customer. Like, do we have a MSA in place? And so then over here in a quote, we move forward and we start to have number and SKUs of what we think we need to ship. We've already done some checks against product catalog and sales goals. And lastly, we get into pricing and legal T's and C's. And, just for fun, we'll say that there was an agent 7 to top this off. And, agent 7 maybe operates up here. And, when we get our 3 processes completed, agent 7 creates our quote in a really nice format, in a way everybody's going to like. And that's how we meet our goal. So looking at this example, I think what we can see is that both approaches, the agentic orchestration and the robotic process automation are ultimately geared to increase productivity by automating these low-value tasks so that our teams can focus on the more high-value goal here of increasing revenue. And so, going back to the conversation that I had with my friend, when you really start looking at the richness of what can be done with agents and orchestration versus RPA, we really see this as a paradigm shift in what's possible as opposed to an incremental step forward.